so proud to introduce our next speaker. He's going to be talking about how to look at your pipelines. His talk is called Why Models Break Your Pipelines and How to Make Them First-Class Citizens. Please give a warm welcome to our speaker.
Hi all, I'm Everett, and I work at Daft. I'll be talking about a couple interesting topics that are relevant to all of us that are working with open source models, working with large language models. A little bit about myself. I was previously an aerospace engineer working at Boeing. I grew up in the area. If you're familiar with Tillicum Middle School over in Lake Hills, or I grew up here, like just honestly like right down the road, which is pretty crazy. I'm now located over in SF, yeah, I started my career out in as a flight controls engineer. And then I steadily made my way further and further into software, developed some data tools in MATLAB, and was like, oh my gosh, this is great. And you've got that like table window in the top, and then like that's where data frames started to feel like really native. And it's like, okay, this is great. I actually can see what the heck I'm doing. Gradually made my way into automotive and worked at Lucid Motors on their big data team, working on a fully open source stack at petabyte scale. A lot of Spark, working with Hive, at a project with the team to transition from Hive to Iceberg, where we saw some crazy cost improvements. Nowadays, I'm working on Daft, which is an open source project, and we'll learn a little bit more about that here in a bit. But currently solutions engineer. I help build out the documentation, build solutions with our clients, and make sure that anybody who's looking to onboard with Daft and our data engine can easily do so. So Daft is an open source project under Apache 2.0 license. It's a high-performance data engine providing simple and reliable data processing for any modality and scale. That means that we have like a native image data type, we handle tensors, and we're like hyper-focused on making it super easy to prompt and embed text or images. And I think my personal goal would be able to like fill out the full like Hugging Face tasks pipeline, but it's a big list. So we've got a quick agenda here, but we're going to just dive into it. So if you take away anything from this talk, it's that models break your data pipelines. And when I talk about pipelines, I'm talking about these jobs at your company or that are running on your servers that are in the background. They're pushing a lot of data from some source to your tables in some structured way. And it's because models are big, they're expensive, and they're stateful. And that's really different from a lot of the analytics workloads that we're used to, where we're just reading and writing from Kafka or into an open source format, maybe a database like Postgres, where we're just using strings and numbers and normal types. I love this PyData conference because it's just the combination of the two things that I know the most and I'm the most excited about, which is Python and data. Python is the largest ecosystem of AI tools and frameworks for good reason. Python's really kind of slow. So we end up implementing like the underlying performance in like C or CUDA or Rust, and there's a couple reasons for that, but we get the composability and declarative syntax of Python, which is amazing. So then we get to go across languages and use amazing in-memory formats like Apache Arrow and things like that, which Daft is native in. So I think the demographic for this conference is mostly composed of like data scientists, data engineers, maybe AI, ML engineers. And we like to develop locally because having to go and like have the infra team spin up a cluster is a pain. Or maybe you're gonna like go and spend a bunch of credits on it and much rather just like work in a notebook, move quickly, see your data, work through all those errors. And we use data frames or SQL to get that done. Great. We're all on the same page. I probably use data frames like way more often than I need to. I try to do things in data frames that I probably shouldn't be, but that's just me. When we want to scale, we'll go and use something like Spark or Ray. Daft scales on top of Ray, but it includes some core primitives and some advantages on top of that that make it more performant. The core of Daft is written in Rust, so you can develop not only locally, but it also goes and works distributed as well. Daft set the world record for reads and writes on S3, and so the I/O performance is really solid, especially on object store. Okay, so we all know ETL. We read, we do something, and we write it back to our tables, our databases, our buckets. Maybe along the way we're checkpointing so that we're keeping track of the job, or it's our different stages are going through all of that. And for the most part, if we can maintain all of our transformations, all of our reads and writes in a single framework, then it's going to be the most performant. And that's kind of where things get more complicated when you try to move into AI/ML using models. So, traditional data pipelines have these deterministic operations. We know that when we multiply or add a few different columns together, they'll just work. We might have memory errors or things like that, but those types of considerations are things that we get to tune as a part of the job. Eventually, if you're working at an enterprise, you're looking for maximum cost performance, where you're looking for not just the ability to push data through and get the job done, but then to lower your costs as much as possible. And just on the last slide, a lot of the time it's batch oriented, because then you can spin up all of these different machines and then saturate them, get that high GPU utilization, because a lot of organizations go and purchase GPUs with on a contract, and so then every time, all the time that you're not using those GPUs, you're wasting money. The data is also structured. We've got schemas, and that makes things easy to scale. Usually when we go and implement something that your Spark expressions, or maybe in Pandas, it doesn't have some sort of vectorized API already in place, you use something called a UDF. So I'm going to give a quick crash course on what a UDF is, which is a user-defined function, and it's exactly what it sounds like. UDF is a piece of custom code that you define in Python to run in your distributed system or in your framework. I'm going to quickly go over what the current market of UDFs are in the industry, and simply because they help bridge the gap between, I already mentioned this, your data frame methods and the thing that you actually need to do. Maybe it's parse a bunch of text and you need some specific regex or something. Yeah. Okay, so PySpark. PySpark has two different ways you can go and run custom logic. There's definitely one that's better than the other, but we're going to go over both of them. So PySpark scalar UDFs, I've got a little usage example over here. I do have a lot of code in this presentation, and so hopefully you guys like usage examples. It's what gets me excited and out of bed every morning. So it's a row-by-row execution. We've got, we can define some Python function, then we decorate it, and then that magically makes it work in Spark. Scalar UDFs aren't great for performance, but there is a better option for PySpark, and this is mostly because of the serialization overhead, which at scale gets really expensive. And so these are stateless functions, right? They're just sending data through. They're not saving anything internally. So Pandas also works with Spark. I think I was looking at a talk from 2023 where they were introducing like Pandas UDFs over on Spark. And these are much faster, much more, they can take advantage of the vectorization inside of Pandas, as well as near zero copy reads and writes with Apache Arrow, which is great, building on top of the ecosystem. Ray. How many people know what Ray is? Okay, so that's important. Ray is a distributed computing framework. It's built on an actor model, which is different, fundamentally different than Spark. And it's great for things like reinforcement learning. And it's probably more popular with data scientists than data engineers. In fact, maybe you're a data engineer or a data scientist in your organization, and you're trying to convince the other team to move over, and vice versa. That tends to be what happens. But Ray has been making some progress in AI, and that's one of the reasons that Daft is able to scale on top of Ray, and we've chosen to do that. Ray is also Apache Arrow native, which is huge. That gives you the zero copy reads and writes SIMD optimizations. But for Ray, Ray has this a particular package that's specialized for large-scale data operations. That's Ray Data. Ray Data has these things called UDFs, and it works with Pandas, where you're mapping batches of data in order to perform your map operations in your map reduce. This is more scalable, arguably, than the Pandas UDF in Spark that we just talked about, on top of the other advantages that we mentioned. And again, these are also stateless, but specifically batch. There's a couple other things that Ray does under the hood, like pipelining, taking advantage of the fact that you can schedule specific tasks and parallelize them. It takes care of a lot of things under the hood. So Daft also has UDFs. But one of the things that we've really focused on the team is filling in some of the gaps that we've seen across the ecosystem. So I'll show you at least just what the first equivalent is for these other UDFs. So define a simple Python function, however you might like to do that. We have a couple inputs. You can just use normal Python type hints. You could also use the explicit Daft type hints as well. And we just released support for pydantic types, which is pretty crazy. And then, so in this example, we load this dictionary from Python, and then we perform this function on top of it, and this works locally or distributed, and there's no code changes. So these are row-wise operations, not batch. That's helpful for a couple of reasons if you're just looking to simplify the way that you're composing your functions. Maybe if you prefer writing your functions in batch, you would enjoy the batch side of things that I'll go over in a second. But we also support async methods or functions, as well as generators, which are a primitive that I think have kind of been neglected, but are super powerful, especially if you're trying to emit chunks from like a video file or audio. And then, of course, we've just, with a small decorator change, then you can adjust your Daft function UDF to batch, where you're inputting a series similar to Ray Data or with Pandas. So model inference pipelines are fundamentally different because inside that UDF, you've got, first off, clarifying, in traditional ETL, we're extracting from some source, transforming it, and writing it. That's, we essentially see that the transformation stages, we've got this pre-processing, inference, and then post-processing, right? But that inference stage is probably happening on a GPU. It is going to have to be stateful because you're going to have to load the model into that function, initialize it, configure it. Maybe you want to do some quantization. And then you're going to do your forward pass, right? And then afterwards, maybe you have to segment that data so that you can eventually write it back to storage. It's important for us to distinguish between online and offline serving. So online serving is what we're all familiar with when we go and interact with OpenAI. We send our chat completions over to OpenRouter, and it's a request response. You can make it faster by sending responses or requests concurrently with async, or you can do streaming. And that's much more focused on user in the loop or agentic types of tasks. And those are optimized for latency. That also gives the server side the ability to centralize state as well as do some cool things like model paging and optimizing memory in a KV cache. And that contrasts obviously with offline inference and offline serving, which VLM has online serving with an OpenAI client. That's a thing, but you're sending things over OpenAI through the client at least. So when you're doing inference either through transformers, VLM, SGLang, or TensorRT LLM, even Triton, then you're probably going to be not only containerizing that, but you'll be batching your inputs so that you get the maximum throughput and you saturate your GPUs for highest utilization. This helps you lower your cost performance, or maximize your cost performance as much as you can, lowering your costs so that you're taking advantage of all that compute. You can also maximize your throughput from disk into your compute at the I/O level. So we've got services and pipelines. So when I'm talking about pipelines, I'm talking about offline serving. There are some challenges or failure modes that are commonly associated with online and offline serving. We've got any types of network instability is going to mess with your requests, whether that's a corruption across the massive data URL that you're trying to pack for images, or you get rate limited, different types of bad requests, and that's because you're sending all of this data over the network. Whereas you're able to co-locate all of that and send it through compute directly if you're doing offline serving, which is why you also run into resource contention. You can and then your whole job crashes, and you also need GPUs, which are in short supply and expensive. You also have to go through all the configuration headaches of matching a model to that particular GPU. And so throughout all of that, there's a bunch of configuration headaches. I think I spent a solid week just trying to get Gemma 3 to work and be configured, getting between figuring out the completions, the API calls, and then making sure that I was using the right GPU on it. And each time it's a 7-minute serving cycle, right? So I can go and probably talk about this for hours and hours, but I can just throw this up here, and there's a couple other deeper details on how your cost is tracked in terms of online and batch inference, but I'm just going to move on. Okay, so when we talk about AI inference, a lot of the time we're just going to, people think about LLMs and using in text generation, but AI ML is a huge ecosystem of different tasks. And so we don't just have text generation or multimodal text generation. We've got classification, we've got embeddings, we've got diffusion models, all of these different modalities and combinations of data and the different things that we want to do, whether it's object detection, segmentation, masking, especially for maybe just your AI meeting notes. You're going to do transcription. But if you're going to do that, you also need voice activity detection and speaker recognition and speaker diarization. All of these different tasks are what actually goes into a production pipeline to get an answer out. You can't just run Whisper on your audio data and expect it to work. It only works on 30-second segments. And so that's why you end up running a UDF, because you have all of this custom code, and everybody has these custom use cases. And at the end of the day, though, what's the most complicated are these multimodal use cases where we're doing text generation. We're not just doing a single forward pass on a certain number of tokens where text generation is fundamentally more compute intensive, more memory intensive than a lot of these other workloads. So the first major complication with text generation is just the models. They're huge. And loading model weights, even for small models, can take some time. They reach into the gigabytes within a couple 100 million parameters pretty easily. And so then if you're talking about a frontier model, maybe any of the larger ones, you not only have to shard those models across GPUs, but then we're having to worry about different types of inputs and being able to pass that data in. So that's why we have those pre-processing steps, those post-processing steps, to be able to handle all the determinism headaches that we run into when we're running text generation models. At the end of the day, a lot of what most companies are running is text generation, embedding, classification, and segmentation types of workloads, and those all look very different, which is why it's hard to go and build APIs for them at the distributed level. So big models break pipelines. Remember, that was one of the first points that I had to mention. Let's look at, as of yesterday, what the top models on Hugging Face are. So the AI hype cycle moves fast. But as of right now, Kimi K2 thinking is the top model. It is currently state-of-the-art in the Humanities Last Exam, which is pretty incredible for open source. It also has 1 trillion parameters and 384 experts. They lowered the number of attention heads, raised the number of experts. They have int4 quantization, and that gives them a major speed boost, a lot better throughput. But again, this is a giant model. And just to give you a feeling for how big that is, the minimum recommended configuration for compute for this is an 8 by H200, which gives you a massive amount of memory. And the model itself takes up 632 gigs, where each H200 has 141 gigs of RAM. Okay, so just think about initialization for a single node. It's an entire cluster just to be able to run this one model. Okay, so yeah, that's 62 10 gig files that you're going to be loading on and sharding with tensor parallelism of 8. That's expensive. It's not just expensive for your memory. It's not just expensive for the amount of time that you're cold starting just to spin up those GPUs and make sure you're connecting to them and deploying, as well as the model initialization and configuration. And so we don't use Kimi. We use something like Gemma 3, which is maybe 4 billion parameters and supports multimodal inputs. It's maybe only 9 gigs of weights, which still takes some time. But we, at the end of the day, are more interested in just getting something working. As you scale up, you get better results on reasoning or science and code, but they start to fall off as you get bigger and bigger. So 4 billion actually turns out to be a decent model. And so if you go to the Transformers page for how you go and run Gemma 3, it looks something like this. And this is a lot going on into it, especially at that pipeline initialization stage where we're downloading the model weights, we're configuring it, and initializing the tokenizer. We just have this message list that we're piping in and we're expecting an output. And that makes this type of an operation stateful because we have to do that initialization. DAF UDFs don't just include the async generator and batch functions. We also support stateful user-defined functions. And this is a key part of our strategy to be able to support all of those different tasks as we build out native support for more of these AI inference use cases. Okay, so toss the pipeline initialization in your init inside of a class, and then you call the inference on in your call method. If you're using DAF, then all you do is you decorate it with daf.class. And then there's obviously more configuration that you can do. If you're using VLLM, maybe the syntax doesn't change, honestly, all that much. And then you get to take advantage of all of their innovations on that front in the CUDA kernels. Another example for the transcription, is we can actually take a look at the anatomy of a UDF. So here we've got a couple different sections, right? So we've got our imports, we've got our decorator, we've got our initialization, and we've got our inference method, right? And so what's helpful about these is that we initialize the gigabytes of weight, so we do it all for one worker, and then that one worker is able to parallelize inference and reuse that. So we amortize the upfront cost of spinning up this inference UDF by leveraging this stateful pattern. Okay, so our inference actually involves forward passing the model that's already configured. It's highly parallelizable, highly distributed, and we're able to pass in things like expressions since DAF is lazily evaluated and perform a lot of the optimizations on the query plan and logical plan. You can also pass in scalars or just arguments, and you can distinguish that in pure Python. So a quick highlight here on this transcription. If you take a look at that input, we've got this thing called a daf.file, which is not something that a lot of people who build with data frames are used to. So if you're trying to work with audio files, PDFs, or video files, and you're trying to emit video frames, audio frames, different data, you can read inside of a UDF and then emit that or batch it together and perform your inference. The quick plug for Faster Whisper is that you can pass in as long audio as you want. It does the automatic voice activity detection and we'll segment that for you. It'll remove silence, and so then makes this inference function nice, and we can just pass out the segments and stuff like that for our downstream use cases. Lastly, we've got the configuration of that actual decorator so that we can configure that worker. We can describe how many GPUs we want to send for this particular worker, the max concurrency, retries for how we want to handle errors, as well as if we want to use a separate process to kind of hop out of the Python GIL lock that is a pain, to say the least. Okay, so making models a first-class citizen is not easy. It genuinely involves creating dedicated functions for each one of those tasks. And initially, a lot of these are currently implemented as UDFs because as much as this stateful UDF pattern is a major advantage, it works locally as well as distributed, and you can move faster as a developer. The reality is you need native integration at the scheduler and distributed layer. So we can demonstrate some really solid performance with our AI native functions. And there's a couple bullet points on why they're advantageous. besides the composability of it, the capacity to actually perform these operations in a vectorized context like a data frame. We include functions for prompting, which is OpenAI chat completions or responses, as well as VLLM, embedding text, and handling those dimensions and the tensors for you. Then you can sync that to your favorite vector database, classifying text, and these kind of follow the conventions of what the transformers library uses, embedding images, which is extremely memory intensive. Daft is super good at that. And then classifying images as well. But again, UDFs are a duct tape solution. So there is prior art, right, in the ecosystem. Ray has a tight integration with VLLM to perform batch inference, and it up until especially recently, they were demonstrating really, really strong benchmarks, and this was effectively the best way that you could go and run batch inference. Recently, the team at Daft worked on a really cool workload, which is currently experimental, but it's we're pretty excited about the results. And it's a new VLLM prefix caching provider for prompt, which takes advantage of like our Rust operators to go and schedule and perform some optimizations for some of VLLM's advanced features like prefix caching, which helps to keep that chat history that you keep building up in your context inside the cache, and so we get not only a higher cache hit rate, but we also see a speed up of 50%, which is pretty insane by avoiding a global sort. So that's pretty cool. There's a whole blog post on that if you want to check it out on the website. But at the end of the day, it's not just that you need to be able to work from your UDFs into native implementations that are working with these inference engines like VLM or SGLang, but additionally that you can read and write from all of these different types of from data sources and syncs. So let's say that you've got all of your enterprise data in Iceberg or in Delta or in Parquet, or just CSV files and JSON. Like you should be able to just read from that, do so locally or in a distributed manner with minimal code changes, and as well as be able to leverage the models you want when you need to. And Daft is rapidly expanding those native implementations across providers, and we're pretty excited. We're cloud native as well, and we're also hiring. So hopefully you guys learned why models are breaking inside of your pipelines and a few patterns to help you fix that. You can join our Slack community, learn more about our open source project, and then you'll find me there, ranting and raving about all of our releases because I just get psyched about building AI functions all day. So that's it. Any questions?
What questions do we have? I have a question for you. I'm curious about what challenges you faced over time as you're developing Daft and bringing it to where it is today.
Yeah, I think that there's a lot of major architectural challenges at like the core engine level that have to get solved before we were really able to reach this API layer where we're saying, now we have just this like one-line thing that can do embed text. Now we have this one-line thing that reads from Hugging Face datasets or reads files inside of a UDF. We had an initial implementation of UDF that's now considered legacy, and so this next generation is much more performant, has new features. I think that transition from and like the long-term investment in the architecture takes time, and that's probably the hardest part is like really being able to wait and make those difficult decisions up front. Yeah.
Any other questions? I have a follow-up to that. Like, how long did it take for you to bring it to this level?
So DAF's been in the works for several years now. I'd have to look back at when the first commit was, but Jay and Sammy, our co-founders, were working on Daft. They were frustrated as engineers working on like autonomous driving software, dealing with multimodal data, and them and all of their engineers were like figuring out infrastructure and like data engine stuff with what we thought were like really solid frameworks at the time. But instead of just like building the pipeline to do like the engineering work, they were working on infrastructure. And so it's you can see all of these like cloud native integrations and things like that. And now I think 2023, maybe late 2022. I have to look back and check when the first commits were. But yeah. Cool.
All right. Well, if there are no other questions, let's thank our speaker again.